What's a phase? It's a state of matter. What are the states of matter? Solid, liquid, gas, plasma. Good. There's one more. A Bose-Einstein condensate, of course. These are the common ones. These are the ones we're going to use. Everything has to do with how tightly atoms are attracted to each other. When they're strongly attracted and they're not moving too fast, they stick together. We call that a solid. If they're moving faster and they break apart, we call that a liquid. If they are able to free themselves from the group and go out on their own, we call that a gas. If they are moving so fast that the protons cannot hang on to their own electrons, everything becomes this subatomic slurry, and we call that a plasma. Okay? So, for example, in super, super hot reactions, at the center core of a nuclear reaction in the sun, we have plasmas. Those are not common states of matter. And on the other end, when things get so cold, certain things like liquid helium turn into a weird state of matter that it's a superfluid. And it doesn't seem to be affected by gravity, and it flows over and out of containers and all kinds of weird stuff. So we're not going to worry about that. We're going to worry about solids, liquids, and gases. Okay? So let's quickly review a little bit of chemistry here. What the heck is a solid? Well, the idea is that between atoms, there's a very weak attraction. Anybody know what the attraction between two atoms is called? You chemistry people. It's called a van der Waals force. And it's a weak attraction. So water molecules are attracted to other water molecules by this weak force, called a van der Waals force. Now, if the water molecules aren't moving too fast, and the attraction isn't too weak, they'll stick together. And we call that a solid. So in a solid, the molecules are locked in to their neighbors by this attraction, this interaction between the two, and they can't move. You know, if you decided to name that molecule Bob, and you came back an hour later, Bob would still be there. Bob is not free to roam, okay, in general. He's locked in. Now, does that mean they're not moving? They are moving. They're just not moving fast enough to break away from their bond. So they are a solid. They have a fixed volume. They have a fixed shape. Okay? There are many kinds of solids. You guys study this in chemistry. There's covalent, or which we sometimes call molecular. There's ionic bonds. There's amorphous solids. There's weird things called quasi-solids. But generally, solids have their atoms locked in, even though they're moving. Okay? What happens if you add some heat to this? Fire. What do? They move faster. And when they move fast enough, they can break away from their neighbor, and now they can still move, they can move around. They don't have enough energy to leave the group, but they're not locked into their neighbor, and we call that a liquid. So with the liquid, if you called this Bob, you'd have to watch out, because Bob can move. He can't leave. He doesn't have that much energy, but he's got enough energy to not be locked into his neighbor. So we call that a liquid. Liquids have fixed volumes, but they don't have fixed shapes. Okay? If you change the shape of the container, the liquid would change shape. But they still hang out together because they're weakly attracted to each other. Kind of like freshmen in the first week of school, right? You just see these freshmen in these big groups. They all stand together in these groups. They go to the bathroom in groups. They go to the cafeteria in groups. Like, freshmen don't walk alone. They're not that brave. They're scared of you guys. They stay with other freshmen. There's safety in numbers. That's like a liquid. They're not locked in, but they don't have enough energy to leave. Okay? Some interesting things. Corn and sand sometimes are solids, but they act like liquids. So one of the things that people tend to do, which is a bad idea, is jump in a grain bin. What happens if you jump in a grain bin? You die. Yeah, every time. You can drown in corn. So, if anybody, there's a truck parked there in the fall and it's full of grain, and somebody says, hey, let's come and jump and swim in the corn. You can't swim in corn. All you can do is drown and die. So it's called grain entrapment, and it's a fairly common way to die on a farm. What happens is when you fill your silo up with grain, the top layer here, because of the humidity, forms a crust, and as you start to drain out the corn, the top doesn't go down because it's made what's called a bridge. And so you would send your son in there to tamp it down, to jump on it and knock the bridge down. Well, if you don't have a good harness on, you can fall in and become entrapped and die.
Isn't there ladders on the inside?
You gotta get to it, right?
Yeah, but like.
You can't. Corn, when you're under corn, you're suffocated.
What if you're fast enough? Like as soon as you fall in and you're just like.
You think you're gonna swim through 8 feet of corn to a ladder? First of all, you're disoriented. You have no idea which direction the ladder is. You can't see, it's dark. You can't breathe, you're panicked. And you've probably gotten turned as you fell. You have no idea which way the ladder is. So, of all the bad ways to die, suffocating and drowning in corn is not on the top of my list. Okay? But in farm country, every year there's 10 or 12 deaths in the Midwest and most of it is practical jokes. People think it's funny, let's go jump in a bin of corn and swim, right? Doesn't work out so well. Corn acts like a liquid. All right, gases. So what happens if you had energy to a gas?
So if you jump into the corn, if you're disoriented, does that keep you from being able to swim?
No, you're disoriented. So if there's a ladder, it's dark, you can't see. How would you know which way to go? So even if you could swim through the corn, which is immensely difficult, you wouldn't know which way to go because you're disoriented. It's dark and you don't know where the ladder is. There's only one ladder. They don't have a ladder on it, every 2 feet.
Someone once told me that if I got trapped in like a big pile of snow to spit and see if I was facing up or down. Could I do that with corn?
You could.
Boom.
What's that going to do for you?
Tell me where I'm going.
There's air.
All right. So if you add energy to a liquid, the molecules move faster. And if they move faster and they move fast enough, they can break away from the group and they become a gas. We call this the kinetic molecular theory of matter. We understand matter and its states, solids, liquids, and gases, as the interplay between two things: the kinetic motion of the atoms and their attraction to each other. At 350 degrees Kelvin. So if you're at 350 degrees Kelvin, there's no degree there, and you are water, the attraction is strong enough to hold you to the group. You are a liquid. Okay? It's not strong enough to lock you in, but to hold you to the group. So you're a liquid. But for gold, the attraction is much stronger. And so at the same temperature, gold is a solid. Because the attraction between the molecules is stronger. And you've got to get hotter than that to make them break the bonds of that. Okay? So we understand the states of matter and the freezing point and the boiling point and all these things. We understand it in terms of two things. How strong the interaction is between the molecules and how fast they're moving. Okay? All right. There's a demo there. I'm not going to play with it. You can go to PhET and play with it yourself sometime. It just shows you basically an animation of what I was talking about. Gases are free. They float all over. They're moving fast. You cool them down and they slow down. If you're a fast-moving gas molecule and somebody's making you slow down and you meet another gas molecule, that weak attraction can now make you stay together, can bind you if you're moving slow enough. So as we lower the temperature, gases condense into liquids. We keep lowering the temperature, they condense into solids. All right? So here's some vocabulary you need to know. All right? You probably already know it already, but when you change from a solid to a liquid, we call that phase change melting. You have to write it down if you want. If you know it, no. Going from a solid to a liquid is melting. Going from a liquid to a gas, we call vaporization, which we also sometimes call boiling. Okay? Technically, it's vaporization. Well, if you go back, if you go from gas to a liquid, that's called condensation. And if you go from a liquid to a solid, we call that fusion or freezing. Fusion is the common word. Okay? So what you have to know is that fusion involves the solid-liquid transition, and vaporization involves a liquid-gas transition. Okay? For some elements, like carbon dioxide, you can go directly from a solid to a gas. Anybody know what that's called? Begins with an S. What? Somebody said it, I think?
I said solid.
No. Sublimation. Heard of that? Sublimation, when you go directly from a solid to a gas. And you can go directly from a gas to a solid. It's called deposition. So, don't need to know those. Those are weird phase changes at certain pressures. But all right. So if I stick a thermometer in a beaker and I put it on a hot plate, what'll happen to the temperature? I put some water in there and I put it in the hot plate, put a thermometer in. What's going to happen? It's going to, what's the temperature going to do? It's going to rise, till what? Till it gets to what? 100 degrees Celsius. And then what's going to happen? Everything's just going to stop? The plate is still on. What's going to happen to the temperature? So, we're going to do that. I'm going to take a beaker of water here and put some water in it, and I'm going to stick it on the hot plate here. So right now, it is at 700 milliliters, and we're going to leave it on for a while. Once it gets boiling, we'll take its temperature. So I'm going to tell you what's going to happen, but you don't have to believe me until you go check it yourself a little while later. What happens is the temperature goes up to 100, and when it reaches 100, the water starts boiling. When it starts boiling, the temperature doesn't change anymore. It stays at 100. So if I keep adding heat, and the temperature is not changing, where's the energy going? Where? Into the air? The plate is adding energy to the beaker. It's adding, I don't know, 800 joules every second. But after I reach my boiling point, the temperature's not changing anymore. So where's the energy going? It's going into the breaking of the bonds and setting the water molecules free. Okay? So once you get to 100 degrees, adding more heat to water doesn't change the temperature. It changes the phase. It turns liquid into gas. And if you put that on a very sensitive scale, I was trying to put it on my scale to show you, but my scale gets overloaded with pot plates, so it didn't work. But you would notice that every second you are losing mass. The scale is going down because you are turning water liquid into water gas, and it's leaving. So the mass is dropping. Okay, so here is the big diagram. You should reproduce this in your notebook. This is the phase diagram that we're going to use. So what we've got is temperature on this axis and heat energy on this axis. And there are 5 distinct phases, and you are going to make this diagram for all the problems you solve. Okay? So, when you have a solid and you add energy, it gets warmer. So that's what this is showing here. This is the energy axis. As I add energy, the temperature goes up until you reach what's called a critical temperature, a special temperature. And at this special temperature, adding heat no longer makes your solid any warmer. It starts melting it. Okay? So when you take a solid, like ice, and you start to add energy, it warms it up until you get to the critical temperature. What's the first critical temperature for ice? 0 degrees Celsius. That's where it turns into a liquid. Okay? So if you keep adding energy to the ice, you turn ice into water. Once all the ice is melted and you've got water, what happens if you keep adding energy? The temperature rises. Your water gets hotter and hotter and hotter and hotter until we get to another critical temperature, which is 100 degrees for water. And then if I keep adding energy, I don't get any hotter. I change it from liquid to gas. And if I were to be able to contain all my gas, if I kept adding energy, the gas would get warmer and warmer. Okay? So when we add energy, when we make the molecules move faster in a substance, they go through 5 distinct phases. If they're a solid, they warm up to their melting temperature. If they're at their melting temperature, adding energy changes them from a solid to a liquid. If they're a liquid and you add energy, they warm up until you get to the boiling point. And then adding energy turns them into a gas. Once they're a gas, if you add energy, it just warms them up again. So this whole Q equals MC delta T thing we've been working on, it really is just what's going on in this section when you're changing temperature. If you're changing temperature, the amount of heat is MC delta T. But if you are at one of your critical temperatures, adding heat doesn't change the temperature. It changes the phase. So during these sections, you can't use MC delta T. What's delta T? From here to here. What's delta T? 0. Does that mean you didn't add any heat? No, it means that heat did something else besides making the molecules move faster. It made them break apart from each other. Once they're all broken apart, then you're melted, and now you can make them move faster and faster. Okay? So, how much heat does it take? Well, that depends on the substance. All right? So, here's a table that shows for some common substances a couple of important things. The first thing it shows is the melting point. That's the temperature where it first starts changing from a solid to a liquid. So remember, the table looked like this. The diagram looked like this, and then there's a plateau, and then like that, and then a plateau, and then it went up. Okay? This was a solid, this was a liquid, and this was a gas. Going from here to here was vaporizing or boiling. And going from here to here was melting, right? So, this critical temperature right here is what we call the melting point. For water, what's the melting point for water? It's 0. The second critical point is up here. So this is the first critical point. This is the second critical point. This, of course, is temperature. This is Q, the heat. So that's the melting point. We call that the boiling point. And for water, it's 100 degrees Celsius. Okay? Now, this thing right here is what's called the latent heat of fusion. It tells you how much energy you got to add to convert the liquid to the solid to a liquid. All right? So it's for water, it's 3.33 times 10 to the 5th, so that's 330,000 joules per kilogram. It takes 330,000 joules of energy to break all the bonds in a kilogram of water. That's what it's telling you. So if you want to know how much energy it's going to take, you've got to take this constant and multiply it by your mass. Okay? So, this is the second equation we're going to use. We already have Q equals MC delta T, right? We use Q equals MC delta T anytime we're changing temperature. So on the slants. But if you're on the plateau, you can't use Q equals MC delta T. You got to use this to find out how much heat it takes, how much energy it takes. So Q, the energy it takes, is equal to the mass times the constant. And we're just going to look up the constant in the table. We are never going to memorize it. And this table is linked on all your homework. You've probably been looking at it already. It's the same link that has the heat capacities. All right. So Q equals M times L. M is in kilograms because L is in joules per kilogram. If L was in calories per gram, then you could use grams for the mass. And your answer would be in calories. But that's not how this table is. So we got to use what we got. All right, so Q equals M times L. Now, let's talk about L for a minute. Suppose I wanted to melt some gold. What L would I use? Allison? I'm going to melt some gold. First of all, at what temperature would that happen? Yeah, 1063 is the first temperature for gold. So if you're at 500 degrees, before you can melt it, you'd have to warm it up, right? Now, when I actually get to melting it, how much energy is it going to take for every kilogram of gold? So which one's melting? Is it this one or this one? So here's where you got to know the words. What does fusion mean? Fusion is the solid-liquid transition. What is vaporization? Liquid-gas transition. So if we are melting gold, which one is that? That's solid-liquid. We're going to use this. Take 6.44 times 10 to the 4th, or 64,000 joules to melt a kilogram of gold. Okay? Does that make sense? All right. What if I had helium and I wanted to convert it from a liquid to a gas? Nolan? Can you see that up here? We got lots of good seats up here by Seth. Come on up. Just bring your stuff. You can hang out here. What do you think, Logan? Helium. I want to turn helium from a liquid into a gas. What constant would I use on this table? I want to turn helium from a liquid into a gas. So is that a solid liquid or liquid gas transition? So it's vaporization.
2.09 times 10 to the 4th.
So I need 2.09 times 10 to the 4th joules for every kilogram. What temperature would that happen at?
Negative 270.
Are you estimating
Negative 269.
268.9? Yeah, that's the idea. All right, Nolan. I want to turn copper from a liquid into from a solid into a liquid. I want to melt copper. What temperature will that happen at?
1083.
Yeah, 1083. How much energy will it take for each kilogram of copper?
1.34 e to the 5th.
Right, joules of energy for each kilogram, right? You see how to use the table? So, if you want to know, do I add energy or subtract energy? Don't do this. Don't write this down. Please don't write this down. Right. You're right. If you are going from a solid to a liquid, are you adding energy or taking it away? You're adding energy, so L will be positive. What if you're going from a liquid to a solid? What if I was asking how much energy does it take to turn water into ice? I'm going from a liquid to a solid. I would use, what number would I use? I'm using water. Going from a liquid to a solid. I would use this number, right? But since I'm going from a liquid to a solid, I've got to remove energy, so I'd make it negative. So instead of memorizing all these rules, just think about the diagram. If you're going to the right, you're adding energy. If you're going to the left, you're removing energy, right? Isn't that what you got to do to take water and turn it into ice? You got to remove energy. That's what your freezer does. It removes energy. It takes the energy from inside and chucks it out the back. That's why the back of your freezer is warm. It's chucking energy out. It's called a heat pump.
Why does it take energy though to do it?
What? Because it's not perfectly efficient.
Yeah.
Right. You can't really cool your house by leaving your freezer door open though. Because the energy it's taking out of the freezer is chucking out the back and it'll just come back around, right? Your house won't get much colder if you leave your freezer open. All right, so let's solve a quick example problem. Grab your calculator. I want to take 0.25 kilograms of ice, so a cup of ice, and I want to turn it into water. I want to melt it. How much energy will that take? Go ahead, find a number. Need to move up, Lily? You're kind of squinting back there. There's lots of good seats up here. Yes, Carson, what'd you get? Oh, we'll wait for you. You like old music?
I need to sit somewhere else. I didn't do the life.
What?
Am I away from that?
Just don't pick your nose.
Why?
Need to move up? Got some good seats left. It's by Claire, but
What'd you get?
there is one by Lily too.
No, I want to have somebody.
So define the heat. How much heat you need? Is the temperature changing, guys? No. So you're not using MC delta T. What are you using? M times L. What's your M? 0.25. All you got to do is find L. And so it's ice. So what substance is that? Water in its solid form. And are you undergoing fusion or vaporization? It's fusion transition, right? So you got to find water and go to Lane-needed fusion. So take 0.25 kilograms times this number.
I got it.
Hey, we're picking on Carson.
83250.
Really? You got a mathematical calculator?
Yeah.
You took a question with only 2 significant figures and gave me 5 in your answer? So we're going to use 3.33 times 10 to the 5th, and that's going to give us approximately 83,000 joules. That's how much energy it will take. What if my microwave adds 1,000 joules every second? How long? 83 seconds. That's reasonable for melting a cup of frozen ice. Okay? All right. Grab your computer, find homework 5.